think it was. Top one. Okay. Thanks, Karen. I think so. If I, is it? Yes. So if I stand like, it's good? It's good? Okay. No, I think the mic was coming on. Okay, and if I do this, the mouse can be seen. Okay. So as Karen said, I'm going to be talking about an attempt to tune ferroelectricity into antiferroelectricity. And this is using the techniques that I talked about in the ferro lecture 2 months ago. So there'll be a brief recap there, but if there's anything else, I think that it has been recorded, as Ron's been keeping track of everything. So this work's been done at EPFL. As Karen said, I'm in the group of Nicole Marzari. This was also done with Giovanni Pizzi, and they're both also at the Swiss National Lab, PSI. So I think there's already been a lot of background on antiferroelectrics. I can kind of take advantage of that and skip ahead in terms of the fact that I just want to remind everyone, in case, you know, the coffee break was very, very difficult and not enough caffeine was consumed, that the major difference in an antiferroelectric is you have this non-polar state, which is competitive with these polar states. And this puts you in this position where you have a double hysteresis loop. And what's also been said about this many times this morning is that this makes antiferroelectrics superior for energy storage. So we've talked a lot about this little green regime and how you can optimize that. But what I really want to then focus on is how we can probe the potential energy surface, how these non-polar and polar states can be tuned from the potential energy surface point of view to construct different types of antiferroelectrics. Okay, so this is my little cartoon of a potential energy surface. We have the global minima, so that's going to be whatever our really ground state, low temperature phase is going to be. But otherwise, we have these metastable states. And so my idea is, can we pull and prod at this potential energy surface to then engineer some antiferroelectricity? So maybe it's just not going to be there for free when you have some material, but can we just, what do we have to do to tune it a little bit? Okay, so we're going to map out the potential energy surface using the symmetry allowed templates in this technique I talked about in December. We're going to use barium titanate because what else would we use as a first test case and inspiration? And then can the polar and non-polar states be made energetically competitive by messing with the potential energy surface? So our inspiration, barium titanate, I don't think I have to spend a lot of time on this, but I kind of wanted to put it back up here because this is what inspired us to develop the symmetry allowed template methodology we've used to study paraelectric barium titanate. And really what motivated it is the fact that if you're in any state other than the low temperature rhombohedral phase, you get disordered titanium displacements that point away from the direction of the macroscopic polarization. And so from a first principle side and a modeling side, this puts us in a position that we want to know what is actually a good model for these phases, because these 5 atom structures pose some issues. So just a little, you know, to give myself some credibility, here are the X-ray diffraction patterns that show that you have these titanium displacements, or these are specifically for potassium niobate, because in this paper, sorry, something got a little messed up here, but in this paper from the 70s, the X-ray diffraction were cleaner in potassium niobate, but you have these planes that are connecting the XRD peaks, and this is giving you the evidence that there's displacements of the B site away from the macroscopic polarization direction. So this complexity in the high symmetry structures has been studied extensively with different types of models, and starting with first principles, parameterized models even back in the 90s. But we added a little bit to this, and we looked at some Carr-Parnello molecular dynamics. And what we could see there very clearly is that the central titanium in this octahedral cage will displace along the local 111 directions. So this is a little histogram of where the titanium likes to sit, projected onto one face of the cube that sits in the middle of this octahedron, and really telling you that the titanium is going to these 111 directions. We also looked at this with the machine learned potential. And so then we could see this not only in the cubic phase, but in the tetragonal and orthorhombic phases. And also the fact that in the rhombohedral phase, there is no disorder like this. Okay, so back to this first principle side and why we want models that actually are more indicative of these real, these experimental data. So we know that these specific tetragonal and cubic 5-atom structures don't capture the displacements away from the direction of the macroscopic polarization. And if we calculate the phonons, as I think Hugo already showed, even the phonons for cubic barium titanate, there are a bunch of instabilities that occur. So if you want to start a calculation that's really going to use these phonons, this presents some issues. Okay, but conceptually, what do we want out of this? Well, instead of a structure that's this 5-atom structure, we want a structure that captures these 1-1-1 displacements. So you could by hand construct something like this, and you can do this. So this structure was proposed in 2006 in this PNIS, but you can put together 1-1-1 displacements that add up to something that is still has an inversion center. But can we do this systematically? So the method for this is general and just using group-subgroup relationships, but here I'm going to specifically talk about perovskite structure. So if we start with a parent space group, we can look for all the subgroups and we can pick the point group symmetry. So here again, because I'm specifically giving you the example of looking at cubic ferroelectric states, that structure I just showed you before. But we can look for all the subgroups that have a cubic subgroup. And that if we look at the subgroup representations, we get displacements according to the Wyckoff positions. So this is an analysis we can do with programs that are on Bilbao, and we did them with the isotropy package. So concretely, we can see that if we look at all the cubic subgroups of space group 221, for example, we can get this distortion pattern that I showed you before, specifically as space group 217. But the main point is that if we look at the Wyckoff splitting, we get degrees of freedom. So the B site, even though it still has a cubic symmetry, can have these displacements in the 1-1-1 direction. Okay, so this gives us a systematic way to generate all the structures we might want to look at that really direct our search into looking for these metastable states in the potential energy landscape. So for a cubic perovskite, you get 27 40-atom templates. We can do the same thing in the tetragonal phase. I highlighted this also in December, but you have some choice now in what high symmetry parent structure you're looking at. We can again go with the cubic space group 221 and just specify we want a tetragonal point group. We can take the tetragonal cell that doesn't have any polar displacement, or we can even take that tetragonal 5-atom cell that now has a polar displacement. So the one here, the difference between these two structures is one has a displacement of that B site and the other one doesn't. In the end, our templates are all consistent and they all make sense. So between the cubic 221 and 123, this gives us the same results. In the case of space group 99, you just get the polar templates. So that all jives together. But we find in terms of practicality, this is actually fastest to use space group 221. As we have these higher symmetries, when we're looking for superimposed irreducible representations, we have fewer to check as there's more symmetries. So here, just to look for this ferroelectric to antiferroelectric transition, I'm just going to present what happens if we look at the tetragonal and the cubic templates, but for the orthorhombic, as we go to these lower symmetry structures, we get more and more templates. Okay, so now we have these templates. Let's actually do something with them. So we can use them as a starting structure for our first principles calculations. And so here, if we just start with those 27 cubic templates, we see that we get 3 kind of final answers. So most of them go back to the high symmetry 221 structure. And this doesn't mean that this is a stable structure. It just means the distortions we had by symmetry, all we could do is end up back at that 5-atom structure. In some other cases, we find these 2 other structures that in the publication and previously have been referred to with these names of 4+4 and 2+6. And this is just the directions the titaniums are moving relative to each other. But they have this space group 217, which I've been showing you guys before, and then a lower energy structure even with space group 205. So, but we can still see that we're reasonably higher in energy than the rhombohedral ground state, which is down here. And this is showing us that if we take this method and we restrict the symmetry, we can find these metastable states that really are restricted by symmetry and live in a energy sector above the ground state. So we can do the same thing with the tetragonal templates, and we find again a set of low energy states where the calculation kind of gets stuck in. So we're finding the metastable states of the potential energy landscape, or in some cases actually saddle points, but we're just not giving ourselves enough degrees of freedom to realize that those are truly saddle points. And I'll just point out here that if we go back, actually, I'm going to point on the next slide. So if we take the stable templates, so both from the cubic phase and this lowest energy one in the tetragonal phase, which has space group 100 instead of 99. So we can see here, if we look at the arrows pointing here, there's a net polarization up the screen. Whereas when we have these two other cubic states, if we sum up these green arrows, these are still going to give us a structure with some kind of inversion symmetry. So if we look relative to the 5-atom cubic structure, the top energy of that previous plot, this tetragonal structure, which is polar, is 19 MeV per formula unit below the 5-atom one. And these other two cubic states are 12 and 15 MeV below the formula per formula unit below the 5-atom cubic one. So these are starting to get into this regime where they can start to compete with each other. Moreover, these structures are actually dynamically stable as well. So these are really metastable states in our potential energy landscape. And finally, just to go back to the original instabilities we had in the 5-atom, the phonon dispersion of our 5-atom structures, we see that these structures, these actual displacement patterns we're imposing, are related to those phonon instabilities. So they come from the X5 plus and the M2 minus unstable phonons that are seen in the high symmetry phases. Okay, so the point now is we have some information about the potential energy landscape. Can we start messing with the potential energy landscape? So the easiest way for me to do this in a DFT calculation is to start applying epitaxial strain. So here I'm starting with these cubic phases, so specifically the 217 and 205. And I also took one of the non-polar phases from the tetragonal templates that still has some unstable phonons, but is one of the lowest energy non-polar tetragonal phases. And we can see this, how they change as a function of epitaxial strain. And I just want to point out that the cubic structures with space group 205 and 217, as soon as we put this epitaxial strain, are no longer cubic because we've broken the cubic symmetry. But they didn't appear as other points on that scatter plot because in those cases, we were looking at an optimization of both the cell and the lattice parameters. So now if we compare this to the tetragonal polar phases. So here, the two extra lines I've added in for you are the 5-atom structure. So we actually see under epitaxial strain that 5-atom structure, which we already know is not representative of the phase, but we see that just shoot up in energy and it's not actually energetically competitive at all. But if we take that other structure with space group 100, we see that if we put a relatively large epitaxial strain, but we can see that we get to this point where we have polar and non-polar states that have stable phonons that are within 2 MeV per formula unit, and this other structure that still has some unstable phonons, but this one is actually very energetically competitive with the polar state. Okay, so this brings me to my summary, and what I want to point out is that we're using this method of the symmetry allowed templates to really get an idea for the potential energy landscape. And then after that, so here I use strain, but maybe there's other ways we can also manipulate the potential energy surface to tune a ferroelectric into an antiferroelectric by trying to put these polar and non-polar states on the same playing field. Of course, you could do the opposite. So I think here, you know, we've seen a lot about lead zirconate in the last few talks. And here you could also think about using this to do the opposite if you wanted to kill the antiferroelectricity or understand why it's going away under certain cases. So here I was using barium titanate as a test case, but I think also inspired by this morning, there's a lot more interesting places where this method could be a lot more useful and interesting. And we've also seen that I think one thing that will be nice to address with this is looking at other temperature effects and maybe even finite fields to actually help these phases be realized in the real world, and the experimentalists here can maybe partake in some of the fruits of this effort. So with that, I'd like to thank you for your attention and take any questions.
Yes. Thank you, Michele. I am not years so I understand that the long-term state is the current state of affairs. But once you kind of have that current state, is it not possible to move the continuum around the past was what the previously constructed?
Yeah, so I think that will give you a lot of what's right around the rhombohedral ground state. So maybe I'll go back to, I lost the mouse, my cartoon. So if we imagine the rhombohedral ground state really being at this global minimum, if we start moving the titanium around there and we keep some kind of rhombohedral distortion, we'll kind of be probing what's happening right about here. And so it can be very difficult because you have all these degrees of freedom in your cell to figure out how to get over here. And so this was almost going the opposite way. We're taking some high symmetry structure that is actually unstable in our potential energy landscape, or at least a saddle point. And we're saying, what are the symmetry allowed? If we take all the distortions and start distorting, it's just a large problem to do. So we're going to at least restrict ourselves by symmetry and hopefully find these other states that exist on the potential energy landscape that still have cubic symmetry. So I think we could go the other way too. Just this way seems to be the best way to direct it in a tractable fashion.
I read that paper, it shows that my question is that you use symmetry kind of constrained research. And is that possible to certain areas of school? Bigger? For example, like a Harris paper talk about the factor distribution mechanics to make it more strong. Could that be another kind of configuration beyond the symmetry?
So first off, I think also so in that paper, one of the motivating concepts was also to get something we could use in a DFT calculation that didn't have unstable phonons. So the idea is, and you want to keep your life as easy as possible. So we're going to find the smallest cell that has stable phonons. So that was it's very nice to start with the smallest cells. But even for actually the orthorhombic, if you check those 40 atom cells, you still have some instability. So you can use this method in an iterative fashion, then look at bigger and bigger cells, because yes, sometimes it will be too small if you start with the smallest symmetry allowed templates. I think getting to things like domain walls, those would use much larger cells, and if there's still an imposed constraint on the point symmetry, that could kind of kill any domain wall. But if you allowed, for example, you still just want a tetragonal point symmetry, you could still imagine some type of twin domain where, your polarization's like this, and that's still something tetragonal, but the cells would have to get bigger and bigger. And the issue there is that when you have these really large supercells, the degrees of freedom in the symmetry analysis get very large, and this might not be the best tactic to take there. You might just get bogged down in the symmetry calculations before we ever do a DFT calculation. So I think they're using, MD approaches in Monte Carlo could be better suited.
Okay, so I'm going to jump into the question. So at the beginning of your talk, you showed a little bit of the motivation for thinking about these kinds of structures by looking at the distribution of the positions of its titanium. So I agree with you 100%. The parallel phase is average is not that 5 atoms structure in the but in the spirit of some of these comments, it might be interesting, you probably did this to look at inter-site correlations. Just wait a minute. you know, that, if you're trying to, if you're capturing, you know, representative states and states, the key phase, you might want them to turn into the spirit of the quadrant and the supercells, where you use not only the average, but also, the first neighbor kind of relations. And I don't know how they do supercells, it's gonna take me to do that.
Yeah, so we haven't looked directly. So in some of the MD simulations, they were looking at the correlations because you see there are these well-known kind of the central peak and these correlations that happen over about 5 to 6 cells, I think is kind of also experimentally. I think this has now even been seen in like real space. So I think that gives us, at least we know our supercells would have to be much bigger off the bat to do that. So I think right off the structure I have, and that's why we say it's good to model the ferroelectric phase because we know we're missing that. And I think it would be interesting to see if you could see it in these cells that are bigger. I'm not sure if it's the best use of the time right now because I think it comes out more easily from an MD simulation. So we haven't looked at that directly, and but I think also you can see the modes that are at play that are also involved in those correlations.
Great step in the right direction. All right. Thank you, Michele, for the talk and the discussion.
I want to do both.
Yes.